So let's keep going where we were talking about alkenes and properties and stability. And so the reason alkenes are a really important functional group because the carbon-carbon double bond is easily converted into many other compounds. As you will see when we get to chapter 10, you'll be shocked at the number of reactions that we can do with alkenes. So being able to make alkenes from alkyl halides is a really important skill. So by the time we get to chapter 10, we're going to be making alkenes in one of mostly two different ways, and then doing reactions on alkenes. So we got to get to that point first, though. So you can synthesize drugs, pesticides, other valuable chemicals, but by far the largest thing we use alkenes for is making polymers. Okay, so billions of pounds are used to make polymers. So all of the plastics that you have everywhere, that's all from alkenes. Polymerizing alkenes. All right, so in this chapter it's going to be really important that we know relative stabilities of alkenes because we're going to be making alkenes and we want to be able to predict, sometimes we can make more than one alkene and we want to be able to predict the best one, the one that's going to be our major product. And so we need to know a little bit about stability. And so one way we can figure out stability is to use elemental heats of hydrogenation. And what we do is we take an alkene. This is a reaction that we're going to talk about in chapter 12, so you don't need to know this reaction right now. But what we do is we take the alkene and we add the elements of hydrogen across the double bond. So the double bond goes away. So this is an addition reaction. And the double bond goes away, and we can measure how much heat is given off because the product is lower energy than the starting material. So we just measure, this one's dead. Okay. Usually lasts a quarter. I'll change the batteries and get that to you. Okay, so we just add the elements of hydrogen across the double bond right here. And the double bond goes away, and so we have the hydrogen, and we measure the heat of hydrogenation. And so what we're doing here is we're just doing that exact thing. We're measuring the heats of hydrogenation for each of these alkynes and these alkenes, and notice they're all going to be going to the same product. So it turns out that if you do that experiment with this delta H, we'll use delta H naught equals minus 30.3 kcals per mole. If we do the same thing with the second alkene, so notice the first alkene, we have an ethyl attached to the alkene and we have 3 hydrogens. In this one we have 2 methyls attached and 2 hydrogens, and if we measure that we get delta H naught equals minus 27.6 kcals per mole. And then on this third one here, we get delta H naught equals minus 28 kcals per mole. 28.6 actually, kcals per mole. And if you'll notice something here, all of these go to the same product. So that means that if we can actually compare the heats of hydrogenation and see which one is more stable, because we have the same product for all of these. So we have this one here, we have this one here, we have this one, it's all the same. And so what we can do is we can see the relative stability. So this can be showed graphically, and that's really the easiest way to, oh boy, I've got to get the hang of this here. All right, so the first one gives off minus 30. Okay, so that's number 1. We'll call this one number 1. We'll call this one number 2. And we'll call this one number 3. Here's the energy of the product, and it's the same for all of them. Same product. All right, so this one here, number 1, gives off minus 30.3. Oh my gosh, okay. Like I said, I'm getting the hang of this. That's a 30, believe it or not. Minus 30.3. And then the second one only gives off minus 27.6. So if the second one only gives off minus 27.6, it means it had to start off at a lower energy level, right? Because it's always, they're all going to the same thing. So this is number 2. I think I'm pressing the button accidentally, so number 2, that's minus 27.6 kcals per mole. And then number 3, that gives off minus 28.6. So that's actually, that means that must start off a little higher, higher than number 2, but lower than number 1. So this is number 3. And so that gives off minus 28.6. Does that look like I put it at the same level as 1? Kind of? No? Okay. We'll go with that. Okay, so that, what that means is that number 2 is the most stable of all 3 of these. Number 1 is the least stable. Okay, and it turns out that the stability of an alkene increases with the number of alkyl groups that are at this are substituted on the carbons of the double bond. So if we move this up a little here, we can see that for the first one, we have 1 R group bonded to the alkene right here. The second one, we have 2 R groups bonded to the alkene. That's going to make that more stable. This is trans. You'll recognize trans here, and this is cis. And so what we can see is that these guys are both more stable than number 1, but trans is more stable than cis. And that, these are the types of experiments that we can do to figure out what we have going on here. So we could do a bunch of these different experiments, and then we're going to end up getting something that looks like what we see on the next page. All right, turns out that alkenes in which groups are trans to each other are more stable than the corresponding cis alkenes. And you'll notice that all of these slides were made on a Mac, and now that I'm putting them on a PC, it's sometimes scrolling them a little differently. The only way to fix that is to make it into a PDF, but the PDF doesn't have this feature where you can write on it as easily. So if you see something scrolling a little bit differently, it's not a problem. All right, so we can do this with a series of alkenes, and so you can see that we have unsubstituted is going to be the highest energy. All right, so we have unsubstituted here. No R groups are bonded to the alkene. Here we have 1 R group bonded to the alkene, so we call it monosubstituted for the 1 group. And then we have the 2 R groups bonded to the alkene. Cis, we know trans. There's trans right here. This one here is called geminal. Well, the 2 R groups are on the same carbon. Those are approximately equal, cis and gem. There is a slight difference in stability there, but we're not going to worry about it. We're going to call those 2 equal. So cis is about equal to the geminal, then we have the trans, then we have the trisubstituted, and then we have the tetrasubstituted. And so as you can see, the more R groups we have bonded to the alkene, the more stable that it is. So, let's write that down. More substitution equals more stability. And by substitution, we're looking for the number of R groups. So more substitution would be more R groups. More R groups bonded to the alkene. And so that's our trend here. And then these are all 3 of these are disubstituted. And then we'll notice that for disubstituted, trans is more stable than cis or gem. So we just write gem short for geminal. Okay, so trans is more stable than cis or geminal. Questions on those trends? Anybody? Yes?
Did you say that the lower energy too makes it more stable?
The ones that are lowest in energy are more stable, yes, absolute. That's absolutely right. Yeah? We're not going to go into the details of that, but you can talk to me after class about that. Okay? More questions? Anybody? All right, let's look at the mechanism of elimination. So we have elimination reaction. We already were introduced to it. There are two types of elimination mechanisms, E1, which competes with SN1, and E2, which competes with SN2. So we're going to have to keep track of these, and we're going to have to make decisions about what the product is. So we're going to start like I did with chapter 7. I started with the E2, and I'm going to do the same thing here. I started with the E2, and then we're going to move on to the E1. So let's go on to the next page. And again, it's putting this on the top, the bottom of that page. We're just going to ignore that. Hopefully that is not upsetting for anybody here. I can try to fix that. I'm going to try to fix that. Because I think it has to do with these fonts like this. That's not the font that you see. When I use those larger fonts, it's scrolling differently, so I may have to fix that. All right, so this type of elimination for E2 is a dominant reaction of tertiary alkyl halides in the presence of a strong base, and it competes with the SN2 reaction for secondary and primary alkyl halides. So that's kind of it in a nutshell. Let's go into more detail here and see if we can figure out what's going on here. So one of the first things we did when we talked about an SN2 reaction is we measured the rate law. And how we do that is we change the concentration of the alkyl halide, we see what effect it has on the rate. And then we changed the concentration of the nucleophile, and we saw what effect it had on the rate. And if both of those changes affect the rate, then that means that both of those species appear in the rate determining step. And so we do the same thing here. And notice here, I have base written, but that's really the same species. In the E2, it's acting as a I don't know why to do that. Okay, in the E2, it's acting as a base. In the SN2, it's acting as a nucleophile, but it's still the same species. So the most common one, for example, would be ethoxide iron. In the SN2, it's acting as a nucleophile. In the E2, it's acting as a base. And so what that means is that both the alkyl halide and the nucleophile have to, or nucleophile slash base, have to collide in the rate determining step. So that means that the alkyl halide and the base slash nucleophile must collide in the rate determining step. So I do RDS for rate determining step. That's the rate that's the step that determines the rate for a reaction. All right, so here's our mechanism. And so we know that in this case our base slash nucleophile is ethoxide, and we know that it has to collide with the alkyl halide in the rate determining step. And so that's what we have going on here. All right, so in our mechanism here, I'm going to put my lone pairs on all my reacting species. So I'm pretty, the pen is not as good in lone pairs. I'm going to be working on getting that down a little better. But when I have a, because wherever the pen is, it puts a dot there. See? Oh, man. I'll get this figured out. But the oxygen has 3 sets of lone pairs, right? I'm pretty strict in my mechanisms. I definitely ask you to learn mechanisms in my class. It helps you learn the material. And I'm pretty strict about points on a test. So any species that are reacting in a mechanism, and maybe I just have to slow down, but that's a good thing for that's a good thing for you. All right, so I want lone pairs on the oxygen, and I want lone pairs on the bromide, because those are both going to be involved in the rate determining step. So the arrow is going to come from the lone pair. It's going to grab this beta hydrogen. We're going to break this carbon-hydrogen bond. It's going to move over here between these two carbons to make a new double bond. And we're going to break the carbon-bromine bond. So notice the arrow, and it keeps getting rid of that lone pair. So you guys are not going to have to call me on this. You know what it's supposed to look like. See? Now, why is it doing that? I don't know. Okay, but that's got 6 lone pairs. It's grabbing the hydrogen. We're breaking the carbon-hydrogen bond, and that leaving group is leaving. And so that leaves us with CH2 doubly bonded to the adjacent carbon. And we have a CH3. And we have a CH3 here. We also have a conjugate base because ethoxide is acting as a base in this reaction. So we're going to have ethanol. Is our side product. And we're going to have bromide ion. Now, you'll find that when I introduce a new reaction, I draw the side products, and that's the last time you see me draw side products. If I'm asking for the product of this reaction on a test, I just want the organic product. I know that this is organic, but the ethanol is organic, but it's a side product. We're looking at what the major transformation here is with the alkyl halide. Questions on that mechanism, anybody? Anybody have questions? All right, so this type of mechanism involving concerted removal of a beta proton by a base and loss of a halide ion is called an E2 mechanism. So as we talked about last time, let's label what we're talking about here. Let's go blue here. The carbon that's bonded to the leaving group is alpha, and the carbon that's right next door is beta. And so this is a beta hydrogen. Which all that means is it's bonded to the beta carbon. And that's what we're eliminating in an E2 reaction. All right, let's look at the energy diagram. What you're going to see is the energy diagram is going to look a lot like an SN2 energy diagram. So we start off with our alkyl halide and our base/nucleophile. We have an energy of activation for really any step in a reaction, and then we end up getting our alkene, ethoxide, and bromide ion. And so this right here is the overall delta H naught reaction. That's the energy difference between the reactants and the products. And let's draw the transition state. This is not an easy transition state to draw, but let's do it anyway. Okay, so we have the ethoxide coming in. Kind of come and grab the hydrogen. So the bond to the hydrogen and the carbon is breaking. By the way, I usually don't have you draw this on tests. We have a single bond between this carbon and its adjacent carbon, and we're actually going to be making a double bond. So this is dotted 2. So this is a little bit of a beast, this transition state. And now I have to use the eraser. Here we go, because I messed up that. We're breaking this bond here to the leaving group. Are you glad I don't put this one on tests? So a lot going on here. I draw this because I want you to see what this looks like, because we're going to be looking at this reaction. I'm going to show you some animations next time for all of these reactions. So this is our transition state. We have some charges, though, in our transition state. So how do we do that? We look down here. We have a negative charge on oxygen right here, and no negative charge on oxygen here in the product. We also have neutral bromine, and then we have negative bromine over here. So let's go ahead and add partial negative charge on the bromine and partial negative charge on the oxygen. So there's a lot going on in this reaction. It is a one-step reaction. So all of this is happening in a concerted fashion. The bonds are being made and broken at the very same time. All right, so just like I did with the SN2 reaction, I talk about the effect of the base / nucleophile, and then I talk about the effect of the alkyl halide, and then I talk about anything else that has to do with that. And once we know all of that stuff, then we can make predictions about what's going to happen. All right, so the base / nucleophile appears in the rate equation, so the rate of E2 reaction increases as the strength of the base increases. That makes good sense. The stronger the base, the faster the reaction that we're going to have. E2 reactions are generally run with strongly negative charged bases like hydroxide and OR-, so earth oxide. Two strong sterically hindered bases called DBN and DBU are also sometimes used. This is DBN, this is DBU. So these are other bases that you will see in the E2 reaction. Solvent effects are the same as SN2. Polar aprotic solvents increase the rate of E2 reactions. Why does polar aprotic solvents increase the rate of E2 reactions? They don't solvate anions very well. Okay, they don't solvate anions very well. Therefore, the base is not, well, one way to say this is shackled, right? As if you have, it's very strongly solvated, it's going to have trouble getting in there to remove that beta hydrogen. So in order to remove the beta hydrogen, it has to move the solvent that's in between it and the beta hydrogen. And it's easy to do in a polar aprotic solvent, not as easy to do in a polar protic solvent. So it's not shackled with solvent and is more free to react. And by the way, the DBU and the DBN, I don't use those very often, but those are used when you want just an elimination to happen and not any substitution, because the two are going to be in competition with each other. And so these are hindered bases. The SN2 is in competition with the E2. And if you have a very hindered base, what's that going to do to the SN2 reaction? Everybody remember that from chapter 7? The SN2 reaction, if you look at the transition state, we have 5 groups around carbon. It's a very hindered transition state. So anything that's hindered is going to slow that reaction down. So if the alkyl halide is hindered, that will slow it down. If the base is hindered, that will also slow it down. So if we want to favor just elimination, we want to use a base that's hindered. Okay, so that's one of the things we'll be talking more about coming up. So if a hindered base, SN2 won't happen. Will be slow or won't happen. Questions so far? Anybody? All right, let's talk about leaving group effects. There's not a whole lot to say. We need a good leaving group in this reaction. As you can see, the base comes in, removes the beta hydrogen, and at the same time, that leaving group starts to leave. So we need to have a good leaving group, just like SN1, just like SN2. That's going to be the easiest part of this chapter. We need a good leaving group. Okay, and so if you have an alkyl iodide, that's going to be fastest E2 because iodide is the best leaving group. It has the best leaving group. All right, so remember how we look at leaving group ability? We want a very, very weak base. Iodide is a much weaker base than chloride ion. So it's going to be a better leaving group. Simple as that. All right, let's look at the structure of the substrate. So when I say substrate, I'm talking about the alkyl halide. So the alkyl halide. SN2 and E2 reactions differ in how R groups affect the reaction rate. Bulky alkyl halides have an increased rate of reaction. So this is not the same trend as SN2. So SN2, we want the least hindered, right? And in E2, we want the most hindered. The most hindered is going to be faster, and it's going to slow down the rate of an SN2. So for the SN2 reaction, fastest is methyl, followed by primary, followed by secondary, and tertiary is no reaction. For an E2 reaction, tertiary is going to be the fastest. And if you think about it, if you think about a tert-butyl bromide, okay, so you have a carbon with 3 methyls and a bromide ion, there's no way that we're going to get any SN2 reaction. But for a base to come in and remove one of those hydrogens that's on the outside periphery of the molecule, that's really easy to do. Okay, so we have the opposite trend here, and that's important for you to remember that. So tertiary, no reaction with an SN2, and it's going to be fastest with an E2. So that's going to make decisions about tertiary alkyl halides under E2 conditions. That's going to make that easier to decide. So the problems are going to be encountered in the secondary alkyl halides. Those are the ones that are going to be problematic. All right, in the transition state, the double bond is partially formed, so increasing the stability of the double bond with alkyl substituents stabilizes the transition state. And if we have a more stable transition state, that means we're going to have a lower energy of activation. More stable transition state. So TS for transition state equals lower energy of activation. Okay. Lower energy of activation. Or EA. All right, so that means if we just learned about stability of alkenes. If we're making an alkene that only has 1 R group bonded to the alkene, that's not going to be as good as if we have making an alkene that has 4 R groups bonded to the alkene. We want to make this the most stable alkene. The most stable is going to have the most number of R groups. So if we compare these two reactions here, here we have our bromide ion. This is a primary alkyl halide. And then down here we have a tertiary alkyl halide. So why is the primary slower? Well, we're starting to form a double bond in the rate determining step, and if we do an elimination from a primary alkyl halide, let's do that. All right, that time I see it now. I'm getting it here. I'm going to be removing the beta hydrogen on the carbon adjacent to the carbon that's bonded to the leaving group. I'm going to break this carbon hydrogen bond. I'm moving down here. And now I'm going to have the bromide ion leave. So since it's involved in arrow pushing, I'm going to put the lone pairs on the bromide ion. So the bromide ion is going to leave. So it looks like that. And it looks like it's consistently getting rid of one of my lone pairs here. So I hope that's not going to be a problem. Let's try that again. And if I don't move, it'll stay there. Okay? All right, so let's see what the product is. We have CH3, CH2. There's also a hydrogen here. We have a hydrogen here and a hydrogen here. So the first learning curve in this chapter is being able to just draw the elimination product. That's not so straightforward. It's a lot more difficult to do than substitution. So if we do the same thing with a tertiary alkyl halide, now I'm going here, grabbing this hydrogen, breaking the hydrogen carbon bond, moving it to midway between these two carbons to make a new double bond, and then bromide ion is going to leave. And if we do that, the carbon on the right is bonded to two methyl groups. The carbon on the left is bonded to two hydrogens. All right, so we have monosubstituted versus disubstituted. So this is monosubstituted. And I'll just abbreviate that, monosubstituted, therefore less stable. The transition stating leading to the monosubstituted product is also going to be less stable. So, I mean, is also going to be less stable. So it'll be higher energy of activation. This is disubstituted. So we're looking for R groups bonded directly to the carbon of the carbon-carbon double bond. And that's going to be more stable. And therefore, it's going to have a faster reaction. All right, questions? Anybody on? Yes? How did I get the product? For this one here? Yeah, it's very, like I said, that's the biggest learning curve is at the very beginning of this chapter, being able to draw the product. So here's this carbon and this carbon. I'll mark them with a, well, I don't know, I want to do that. We have this carbon here. Let's call this carbon 1, carbon 2, right? And then over here, this is carbon 1, and this is carbon 2. So let's follow what's happening here. And this may be good for me to do, okay? So we got carbon 1 and carbon 2. Here's carbon 2. It has two hydrogens. And it has the third hydrogen right here. We're eliminating that hydrogen. So over here, it's got two hydrogens. We're breaking this bond, moving it over here, and then this group is leaving. And so this carbon here is bonded to two methyls. So there's the two methyls here. Okay? All right. Yes? You certainly can. All three of those methyl groups are equivalent. So yes, you could eliminate a hydrogen from any one of those methyl groups. Yeah, definitely. All right, let's look at regioselectivity in the E2 reaction. And this leads us to the Zaitsev rule. You'll see different spellings for Zaitsev. This is the one that makes more sense to me. But there's many different ways to spell, or like at least 3 that I've seen to spell this. So this is the way I'm going to spell it. When 2 or more elimination products are possible in an E2 reaction, the most stable alkene will predominate. So now you see why we have to know something about stability here. So the most stable alkene is going to predominate. All right, so let's look at this reaction right here. We have, we have ethoxide. We're in a solvent of ethanol, 70 degrees. And I'm going to draw the 2 possible products. And then I'm going to show you how we get the products. Again, learning curve number 1 is just being able to draw the products here. And then some students, so if you're having this problem, some students have trouble seeing what we mean by disubstituted, monosubstituted, so that's very common. So that's probably a learning curve number 1. We'll just put an ethyl right here. So I use ET abbreviation for ethyl commonly. So which of those alkenes is more stable? Yeah, the first one's tri-substituted. Okay, so this one's going to be 69%. And this one's only 31%. 69% more stable. And that's because it's tri-substituted. We have three R groups bonded. And this one is less stable. So di-substituted. So on a test, I will be very clear whether I want all the products or I want the predominant product. If I say I want the predominant product, then you would only draw the first one here. If I say I want all the products, then you would draw all the possible products. Okay, there's one. Okay, so let's see how we get these two different ones here. So we have, and now what it's doing is it's scrolling. It's taking away some of my space here, which we don't like. So maybe I can write off the margin. I think I can write off the margin here. Okay, so for the first one here, let's draw this. Okay, so and then I'm going to have ethoxide coming in. Grabbing the beta hydrogen, breaking the carbon-hydrogen bond, moving it over to the carbon that's bonded to the leaving group. And then we're going to have the carbon-bromine bond break, so we're going to have the leaving group leave. That's how you get this one right here. So you'll want to put this second one on the bottom of your page. And I think what I'm going to have to do is come back and take away all these different fonts like this. They're taking up more space. Okay, for the second product, okay, so we have that. We have the CH3 right here. Now we have our bromide with its lone pairs. So the arrow is going to come from a lone pair on oxygen. We're going to grab the hydrogen. We're going to break the hydrogen-carbon bond, move it over here to make a new double bond, and then the leaving group is going to leave. That will give you this product. Questions? Yeah. How did I get the percentages? Right here? Did I make a mistake? Right here? Oh, that hydrogen should be gone. So let's, rather than doing the eraser tool, let's just scribble that out. Okay, that should not be there. Okay? To answer your question on how we get the 69% and the 31%, we run the experiment and see what we get. That's not, I mean, I wouldn't ask you to come up with numbers. I might ask you what's the major, but I wouldn't ask you to come up with numbers. More questions? Anybody? Okay. Some important points. And here's where we get tricky. The most stable alkene is usually the most substituted. Usually, but not always. Most stable alkene is usually the most substituted, but not always. So let's look at some examples here. All right, so let's look at this guy. The carbon bonded to the leaving group is alpha. And the carbon that's right next door is beta. We have two different carbons next door. So that was one good thing about covering spectroscopy early. Now we're able to recognize when we have different hydrogens. So those two hydrogens are different. So we have two possible products here. We can, and that's because we have two different beta hydrogens. So that's a beta hydrogen here. And there's a different beta hydrogen right here. And so if we draw products from both of those, I'm going to draw a product from eliminating the beta hydrogen on the left, and I'm going to draw the product gotten from eliminating the beta hydrogen on the right. Okay, so that's the product from eliminating the beta hydrogen on the left, and then we also have the product from eliminating the beta hydrogen on the right. Which one of those is the most substituted? First one or the second one? And it may be easier for you to see. I got to stop drawing it this way. It may be easier for you to see if I put the hydrogen in. How many R groups are bonded to this compound here? We've got methyl, methyl, and hydrogen. Okay, so there's three. This one has two alkyl groups bonded to the alkene. Okay, so this one here is the least substituted. So it's di-substituted. And this one is the most substituted. It turns out that this one is actually the major product, the one that's least substituted. Can anybody think of a reason why that first product would be the major product? Yes?
Is it because the benzene ring is contributing stability to the double bond?
Yeah, so did everybody hear what he said? The benzene ring is contributing stability to the double bond. If you had my class last quarter, we talked about the fact that this double bond here is conjugated with these double bonds in the ring. So if you didn't have my class last quarter, that's all right. Conjugation just means when we have alternating double bonds. So we have a double bond here, single bond, double bond, single bond, double bond, single bond, double bond. Those double bonds are all conjugated. When two double bonds have a single bond in between, they're conjugated. And what that means is that we can actually draw resonance structures. That makes the compound more stable. So this one is the major. So it's the least substituted, but conjugated with the aromatic ring. Least substituted, but conjugated with the aromatic ring. When things are conjugated, they're more stable. So therefore, it's more stable. I'm not going to do it here, but you can imagine that we can actually go and we can move this double bonds around here. We can go and draw a bunch of resonance structures because of the location of that double bond. Yeah?
How powerful is that effect? Like, let's say it was monosubstitute instead of disubstitute. That's still the
It's a pretty powerful effect. It's a pretty powerful effect. But I'll try to stay away from those ones where they start to get really close. I try to stay away from those on exams. Okay? Up at the top. It's usually the most substituted, and in this case it's not. Yeah. So usually the most substituted, but not. All right. And we have a second case here. If anybody who has my lab, we did an experiment in the first week. Or maybe you haven't done it yet. Maybe some of you have it today. But in some eliminations, the less stable alkene is the major product. We did it in my lab this first week. You guys are going to, anybody who has 51LB, you're going to be doing it later in the quarter. And so it turns out that if we have a hindered base, I still have one more minute, guys, hindered base and hindered alkyl halide. So this is a tertiary halide. And this is a tertiary base. They're both very hindered. And tertiary base also very hindered. And what happens in that situation is the base is going to remove the most accessible hydrogen. That's the most accessible hydrogen is, we've got two choices here. We have beta hydrogen right here. Beta hydrogen right here. And we have beta hydrogen right here. And here, these guys are all the same. It's much easier because this base is so hindered, it's much easier for it to eliminate one of those outside hydrogens rather than this inside one. And so the major product is going to actually be the least substituted, but we're out of time, so I will draw those next time.